Okay guys, today we're going to continue our discussion of waves. So before we start, I hope that you have your Chapter 8 guided notes out. You're also going to need a calculator. So if you're watching the video, please make sure you have your guided notes and a calculator. So Chapter 8 is about waves. One of the natural phenomena of waves is called the Doppler Effect. And that's what today's lesson is going to be about. And so I wanted to start by showing you a video that demonstrates the Doppler Effect. It's going to be a fire engine. And the fire engine is going to come into, and you'll see it, it's going to go down the street like this. But what I want you to pay attention to is the siren. And more specifically, the pitch of the siren as it's coming toward us. And then when it passes us, I want you to pay attention to the sound. You're going to hear a different pitch as it goes by. And so let's start with that. Okay, so I hope that you were able to hear that. But as it was coming toward us, the frequency of those waves is very high, and so we heard a high pitch. But as it went by us, you could tell that the frequency or the pitch of that siren decreased. And so it was a lot lower pitch as it went by. And so that's what the Doppler effect is. And that's what we're going to be learning about today. So to start off, let's write the definition for the Doppler effect in your guided notes. So the Doppler effect is the change in frequency. The change in frequency and pitch that occurs when the source of the sound is moving relative to the listener. So when the sound is moving relative to the listener, you're going to hear this change in frequency or change in pitch of the sound. So I've got a picture on this slide that kind of demonstrates that. So this police car is moving. Okay, it doesn't say what his velocity is, but he's moving pretty fast. We'll say, 65 miles per hour. Now, as the police car moves, his siren is on. Well, the speed of sound in air is about 760 miles per hour, or 340 meters per second. And so as this car moves, it's kind of bunching up these sound waves from the siren. And so these waves are closer together. And so if you talk about its wavelength here, now these sound waves have a very small wavelength before the car. Well, small wavelength means there's high frequency. So the waves are very frequent in front of the car. And so that's why this guy right here, when he's listening to the siren, hears it at a very high frequency or high-pitched sound. But since the car is moving forward, behind the car, you'll notice the distance between these sound waves now is increased. And so we have a long wavelength. The wavelength is longer here, which means in terms of frequency, the waves are less frequent. So it has a low frequency or a low pitch. And so that is what is responsible for the Doppler effect. Now, if we look at this slide here, it says the Doppler effect only occurs when the sound source or the observer is moving. So the Doppler effect only occurs when there's movement. Either the sound source or the observer has to be moving here. So if you have a sound at rest, so if your source is at rest, so let's say this car honks its horn. Well, that sound wave is going to be sent out, and if you notice, the wavelength in front of the car and behind the car are the same because the car is at rest. So Doppler effect doesn't occur when the car is at rest, or when the observer is at rest. So the Doppler effect only occurs if there's motion relative to each other. Either this observer is moving or the source is moving. So now the car is moving forward, which bunches up the waves in front of it. So this observer would hear a higher pitched sound. This guy back here, because the car is moving away, would hear a lower pitched sound. So in order for Doppler effect to work, there has to be motion. You have to be moving. I've got a demonstration on this right now. I've got a really loud buzzer, and I hope that this works through the microphone. But this buzzer, what I'm going to do first is just leave it on the counter so there's no movement. Okay, and then I want you to pay attention to the frequency or the pitch of this buzzer. Okay, so I hope that you are hearing that, and it stays the same pitch or the same frequency. Let me try it one more time. Again, it's at rest. Okay, so Doppler effect doesn't happen when you're at rest. So now what I'm going to do is I've got a string attached to this buzzer, and I'm going to move it. I'm going to swing it around my head, and so you should hear this alternating high pitch and then low pitch as it moves away. High pitch as it moves toward the microphone, and low pitch as it moves away from the microphone. So see if you can't pick that out. So I'll get it moving around my head here in just 1 second. Okay, and so I hope that you were able to hear when I move the source of the sound, this buzzer, as it's moving toward the microphone, you probably heard the high-pitched sound, and then as it moved away from the microphone, it went to a lower pitch, so it kind of gives this high and then low-pitch alternating sound. And so hopefully that's starting to make a little bit more sense what the Doppler effect is. Okay, I like to always bring up this point when I'm talking about the Doppler effect. So the sound barrier and sonic booms. I don't know if you've ever heard a sonic boom before, but it's pretty impressive. It's a really loud sound, and it's actually a big compression wave, and so it can shake, even shakes your whole house and can break windows sometimes. But what a sonic boom is when something breaks the sound barrier. Like, for example, this fighter jet here. When it goes faster than the speed of sound, then you will hear a sonic boom. And he's got a picture of it right as this fighter jet is breaking the sound barrier here, and it causes this huge compression wave. So let's look at what causes those. Say, for example, the fighter jet is stopped, it's not moving, but the engines are on, and so it's sending out sound waves. But notice, the frequencies are the same in every direction, or the wavelengths are the same, and so are the frequencies. So Doppler effect's not happening when the source of the sound is stopped. Now let's say that it starts flying pretty fast, but it's not breaking the sound barrier, so it hasn't gone faster than the speed of sound. What you'll see if this plane is moving to the right, in front of the plane, because the plane is moving that way, all these sound waves start to bunch up. And so you'll see higher frequency here in front of the plane, and behind the plane, you'll notice the frequency is much lower frequency. Okay, and now when this fighter jet, if it was to go faster and faster, it's going to reach a point at which the velocity of the jet is actually as fast as sound. And so it's going to meet this speed of sound. And so what happens as this fighter jet reaches the speed of sound, now notice all of these sound waves in front of the jet are right on top of each other. And so it sends out a very powerful, if you remember, sound waves are longitudinal waves which have compression and rarefaction. All these compressions are lined up right on top of each other, and it sends out a very powerful wave that if you're on the ground, you hear as a sonic boom, and it can be very powerful. Anyway, that's what's happening with the sound barrier and sonic booms. It's everything to do with the Doppler effect. Okay, so let's continue on with your notes. There's something to write down here. It says when the source of the sound moves toward an observer, so when the source of the sound moves toward an observer, the perceived frequency of the sound is increased. So he hears it at a higher pitch. So the observer will hear a higher pitch. So that's why this guy right here hears the sound at a higher frequency. All of these sound waves are bunched up in front of the police car. Well, just the opposite is true if you are behind the source of the sound. And so that's what we'll look at next. So when the sound source moves away from an observer, the perceived frequency of the sound is decreased. So the frequency is decreased, and so the observer will hear a lower pitch. So that's why it explains this girl, she's behind the police car, she's going to hear a much lower pitch or lower frequency sound wave. Okay, so up to this point, we have talked about the Doppler effect in terms of qualitative observations. Well, if you're in front, you're going to hear it at a higher frequency. If you're behind this sound source, you're going to hear it at a lower frequency. And so we just made some qualitative observations. But this is a great, actually, analogy to physics as a whole. If you look at physics, we hear or we make an observation about what's happening in the natural world. And so we make an observation. We start usually with qualitative observations. Like, for example, the Doppler effect. You hear higher frequencies in front and lower frequencies behind. But if you've learned anything in physics this year, physics, I hopefully have taught you, is that in physics, we love to quantify everything. It's not good enough just to say higher frequency in front and lower frequency behind. In physics, we like to be precise. We want to quantify things. So what we're going to do now in the last half of the lesson is actually quantify the Doppler effect and put a number to it. How much higher is the frequency that this man will hear? How much lower is the frequency that this girl is going to hear? And so hopefully it'll make sense. So let's get on to quantifying the Doppler effect. So in your books, there's a spot for you to write down the Doppler effect equation. This is the Doppler effect equation. It's a pretty cool equation. And so as you're writing that down, I'm going to explain all the variables that are in this equation. It's going to be important that you know which variable is which and what it means, because you're going to have to plug numbers into them. So let's start with F observed. Well, F is for frequency. So this is the frequency that the observer is going to hear. This is the observer, what he hears it at, the frequency. Okay, so that's F observed. Now let's move on to F actual, which we see right here. F actual, F is for frequency, and actual is the actual frequency of the sound source. So what it actually, the frequency of the actual sound source. Okay, V. You see V a couple of places. And actually, I like to write an air underneath both of them. So if you want to put that in your notes, this is the velocity of sound in air. So it's the velocity of the wave through the medium. Most of the time we're talking about sound waves, and most of the time it's going through air. And so if you will make this note, 340 meters per second is how fast sound goes through air. Now this can change. It can be a little bit different than 340, but that's a pretty good approximation on an average day. It changes based on temperature and a lot of other factors. So around 340 is what it's going to be. So all you're going to do is plug in 340 right here and on the bottom. Okay. Our next variable, v_obs, is for the velocity of the observer. So this is how fast the observer is moving. So maybe the observer is also moving and the source is also moving. Well, the velocity that the observer is going, you'll plug in right here. Vs, which you see right here, is the velocity of the wave source. So whatever is causing the wave or the sound is going to have a, if it's moving, it's going to have a velocity. And you'll plug that in right here. Now, very important, this is very important part. I want you to put a star by this. I've got it in your guided notes. Put a star by this one. It says for this Doppler equation, we will use positive values of Vs and v_obs if the motion is towards each other. So if they are moving towards each other, we're going to use positive velocity values. On the other hand, we will use negative values if the motion is away. So if the source and the observer are moving away from each other, those velocity values will be negative. Okay? And I've got a couple of example problems that you'll be able to see how this works. And so let's get to them right now. So practice problem number 21. It says a truck is moving towards you at 20 meters per second. Its horn is blowing with a frequency of 440 hertz. What frequency do you hear? Assume you are at rest and the speed of the sound in air is 340 meters per second. So I know you're starting to learn about the Doppler effect. I'm going to provide you with this equation. Okay, so I will always give you this equation. Your job will be to plug in the numbers in the right spot and then to solve for the variable that they're asking you to solve for. So, like all physics problems, I like to draw a picture. Okay, we've got a truck. I'm not a very good artist, but here's my truck, and it's moving towards you. So you are the observer, and it honks its horn. And like we saw, the horn is going to leave sound waves. And before, they're going to bunch up, so it's going to be very small wavelength or a high frequency in front of the truck. But behind the truck, we know those waves space out. And so what I would like you to do now is predict. If this horn, if the source, so the horn itself is 440 hertz, I want you to make a prediction. Are you going to hear that at a higher frequency than 440 or at a lower frequency than 440? So think about that for a second and make a prediction. Hopefully you're thinking to yourself that since you are in front of this truck and these waves are going to be bunched tight together, you're going to hear it at more or greater than 440 hertz. That's our prediction, okay? That's our qualitative observation or our prediction. Now what I would like to do is go through this equation, show you how to plug in the numbers, and show you how to solve for frequency observed. Okay? So let's plug in. So we're solving for frequency that you observe it at. So I'm going to put f_obs is equal to f actual. Now what is the actual frequency of the sound source? Well, it told us it was 440 hertz. So I'm going to put 440 in for f actual. Okay, now we've got these parentheses. V, like I said, is usually what we're going to be talking about is sound waves in air. And so it's said that the velocity of the sound in air is 340 meters per second. So 340 goes here, plus the velocity of the observer. Well, you are the observer. What was your velocity? Well, it said, assume you are at rest. So your velocity is 0. Divided by the velocity of air, again, it said was 340. This minus sign you have to keep in there, so I'm just going to keep it as a minus. Now, the velocity of the source I'm going to put right here. But remember, if it's going towards you, it's positive. If it's going away from you, it will be negative. So let's figure this out. How fast was the truck moving? Well, the truck had a velocity that was equal to 20 meters per second. It told us right here that the truck was going towards you at 20 meters per second. And so that's going to be, because it's moving towards you, positive 20. So I'm going to put a positive 20 in right there. Notice, I did not change this minus sign. This is built into the equation. We don't change it. Okay, and so this becomes a positive 20, and so you just leave it like that. Now close it off with the parentheses. And so now we have a math equation with just one variable that we don't know, one unknown. It's very easy to solve. Let's simplify it. So F observed is equal to 440 times, now do what's in the parentheses first, 340 plus 0 is 340 on top, divided by 340 minus 20 is 320. Okay? Now let's do what's in the parentheses first. So your frequency observed becomes 440 times 340 divided by 320. 340 divided by 320 is equal to 1.0625. And so let's times these two numbers together now to get our frequency observed. So I've calculated it that it is 467.5. And my units for frequency, what are the units for frequency? Hopefully you're saying to yourself, they are hertz, or waves per second. Okay, so that's what it is quantitatively. Let's go back and compare that to what we predicted. Did this play out as we predicted? Our prediction was that it was going to be, you were going to hear it at a frequency greater than 440. And so yes, it is greater than 440. Now we know exactly what frequency that you will hear this horn at. So that's one example of the Doppler effect in running the numbers through this equation. Hopefully that makes sense. I've got another practice problem for you to try. And so let's see if we got it right. 468 is what they got. So if you rounded this up, 468, yeah, we did it correctly. So, all right, practice problem number 22. I would like you to try on your own. Okay, so if you're watching the video, please hit pause right now and go through this and see if you can tell me what the answer is. Again, I would recommend to draw a picture and then list all your variables, plug them into this equation, and see if you can't get it right. So let me give you a second to try it. Please hit pause and try it. Okay, so hopefully at this point you have an answer. But I wanted to kind of quickly run through this last example with you. So what I've done is I've started by drawing a picture. Okay, it said that the truck was moving away from you at 20 meters per second. So I drew the truck, and it's moving away at 20 meters per second. And so here you are behind the truck now. And it's blowing its horn. The horn has a frequency of 440 hertz, so I made note of that. And then it says, what frequency do you hear? So we're going to solve for the frequency that you hear, which is frequency observed. I wanted to stop for a second and again ask you about your prediction. If you are now standing behind the source and it's moving away from you, will you hear it at a higher or a lower frequency than 440? So make that prediction. Are you going to hear it at a higher or lower frequency than 440? And so hopefully you're saying to yourself, well, you're standing behind it, it's going away from you, so these waves are farther apart, which means they're less frequent. So you're going to hear it at a lower frequency or less than 440 hertz. Okay, but now let's use the Doppler effect equation and actually quantify how much lower, hopefully it is lower, how much lower it will be. So let's run through that. F observed is equal to F actual was 440. Okay, and then we have these parentheses. V air is it said that the sound in air is 340, so that's where I'm going to put 340 in. It's also on the bottom as well, so I'm just going to quickly put a 340 on the bottom. Plus, it goes on top, and the observer, the velocity of the observer. Well, it said that you are at rest, or we're assuming you are at rest. So you're the observer, and your velocity, if you're at rest, 0. Okay, now that might not always be the case. You might get a problem where the observer and the source are moving. So you might have values in both of these places. Okay, on the bottom, notice we have this minus sign. So we're going to put a minus sign in. And now I always like to use parentheses right here. And I'm going to put in the velocity of the source. It said the velocity of the truck was going 20. However, this is where you've got to pay attention. The signs of these velocity observed and velocity of the source can change depending on whether you are going away or if it's coming towards you. So now the truck is moving away, okay, away from you. So remember, if it's moving away, that sign is going to be negative. So I'm going to put a negative sign in here. We don't ever change this one. This one's just built into the equation. That will always be negative. But if the velocity is, and they're moving away, this velocity will also, there'll be a negative sign right there. Okay, so we'll close it up with the parentheses there. And now let's solve it. Okay, so frequency observed is equal to 440 times, we have 340 on top, and 340 minus a minus 20. 340 minus a minus 20. Okay, so again we have 340 minus a minus 20, so that's going to be a plus 20. So 340 plus 20 is actually 360. Okay, so a lot of students will make an error right here. Always remember, minus a minus, that becomes a positive, so it's a plus. All right, now it's a simple math equation. Let's simplify it a little bit more. 440 times, let's do 340 divided by 360 is 0.944. Okay. And so if we times that by 440, our frequency that you are going to observe it at is going to be 415.5. And what are the units for frequency? Hopefully you're saying to yourself, it's hertz. So it's going to be 415.5 hertz is what you're going to hear it at. So let's see if that's kind of makes sense with our prediction. We predicted that it was going to be less than 440. And yeah, that came out to be true. It's less than 440. We got down to 415.5. Okay, very good. Hopefully that makes sense, guys. I think it's a pretty easy equation and formula to use, but you're going to be plugging in. Now you might be solving for the velocity, for your velocity of the observer. You might solve for the velocity of the source. But they would have to give you all the other variables. So we'll just use some simple algebra skills and solve for whatever they don't give you. All right, let's see if we got it right. Yeah, 416, they just rounded this up to 416. Very good. Let's summarize the Doppler effect here and kind of talk about the applications of the Doppler effect. So Doppler radar can be used to determine the velocity of distant objects. And we use this, these radar waves. These are high velocity waves, and we can use them. They'll bounce off the object at a distance and come back, and we can use that difference in frequency to determine the velocity of the observer or the velocity of the source. And so these are used all the time. For example, in radar guns. This is a policeman here has got his radar gun And he can shoot these waves, these high-speed waves at a car, and when the waves are reflected back at different frequencies, what the radar gun will do is the Doppler effect equation and tell you the velocity that the car is moving. So very useful. In meteorology, there's a news station with their weather, they always say Doppler weather forecast. And so they're using Doppler radar and sending out these waves from the top of their building in a 360-degree pattern. And when they come back, they measure the differences in the frequencies, and it can tell you the velocity of the weather in that area, so the clouds. Aviation uses Doppler effect all the time with radar and determining, where airplanes are at in the sky and what their relative velocity is to the airport. And it helps them track and make sure that the airplanes are not colliding with each other. So Doppler effect has many applications, and there's way more than just this, but anyway, it's used all the time. Anyway. Okay, let's finish up. I saw this TV episode the other night. It's on one of my favorite shows called The Big Bang Theory. And Sheldon, this guy right here, is one of the main characters. If you've seen it, but he's a physicist, and he uses scientific principles all the time throughout the show. But on this episode, he was talking about the Doppler effect. And so, kind of a funny episode, and we'll end here. We'll end this lesson on Doppler effect. Hopefully, now that you understand the Doppler effect, you can catch the humor of it. So, let's watch it.
Sheldon, there's something I want to talk to you about before we go to the park.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and Peter Pan, that's so cute.
Actually, Penny, he's wrong.
Not Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Okay, so hopefully you're able to understand the humor in that now. So to finish up, I want to give you some more practice with Doppler effect and using it and understanding it. So I've got a Doppler effect worksheet. It's in your student workbook. So let's go there now. Again, it's called the Doppler Effect worksheet. And let's get that done, and hopefully this helps.